Traditional buildings are anchored firmly to the earth. When the ground shakes, that rigidity tears them apart. To save critical infrastructure, modern engineering does the exact opposite. Instead of tying a building to the rock, it cuts it loose. It's a concept called base isolation. You essentially place the entire structure on a series of gliding isolator paths. The earth can thrash underneath, while the building above practically floats in place. Take the Zuckerberg San Francisco General Hospital. It sits directly on the San Andreas fault line. To survive there, the General traded rigid vulnerability for massive flexibility. The entire hospital is engineered to glide 30 inches in every single direction. But separating a massive building from the earth creates a secondary issue. If the building is cut into independent gliding sections, the floors, walls, and ceilings connecting those sections also have to be physically severed. This resulting architectural separation leaves yawning, fluctuating gaps right in the dead center of the building's busy corridors. Inside a hospital, a sudden 2.5-foot trench opening in the floor is catastrophic. It instantly stops gurneys, crashes heavy medical equipment, and blocks evacuation routes. A trauma center depends on its ability to maintain a sterile environment. An open fissure down to the foundation introduces dust, debris, and contaminants directly into the hospital's primary arteries. How do you build a perfectly flush, perfectly sterile bridge across two violently shifting tectonic plates, right in the middle of a hallway? Maintaining a seamless floor across these gaps requires highly specialized seismic expansion joint covers. This is the multi-axial corridor cover, or the MAC system. It connects the floor, walls, and ceiling covers so they function as one unified cab assembly. Because they move in unison, the entire perimeter can shift and warp without crushing into the surrounding drywall. Down at the floor level, where a 30-inch shift generates extreme lateral pressure, the center metal pan actually lifts completely clear of the moving substructure beneath it to avoid buckling. Yet even with that lifting capability, these components are rated to handle 2,000-pound point loads. Forklifts and heavy medical scanners can roll right over them. The lifting metal pan solves the structural threat of the building tearing itself apart, but it must still be adapted to meet the extreme hygiene standards of a trauma center. We must zoom in on the micro level to see how these mechanical gaps maintain absolute sterility. The joints use specially formulated elastomeric inserts made from self-extinguishing antimicrobial materials that lock into the aluminum channels. Looking at the profile, you'll see a smooth, visible surface with no folds or deep crevices, allowing for rapid cleaning. These specialized gaskets also act as a moisture barrier. They maintain complete water tightness and prevent aggressive fluids or harsh cleaning chemicals from penetrating down into the subfloor. The heavy-lifting structural pan, combined with these flush antimicrobial gaskets, creates a seamless bridge. It protects the building's skeleton while simultaneously locking down its sterile environment. When the shaking finally stops, the building sections are often left displaced, and the joint covers are still elevated. This is where a gravity-activated turn bar mechanism, hidden entirely underneath the floor plates, takes over. Using only gravity, it pulls the cover smoothly back to its normal dead center position. It requires zero human intervention and no mechanical maintenance to reset. The building's mechanical armor is entirely self-healing. The moment the earthquake ends, the hospital is intact and ready for immediate operation. Back in the everyday reality of the hospital, you see none of this. You just see a quiet, polished corridor. Doctors, patients, and heavy gurneys cross these thin flush lines thousands of times a day, completely oblivious to the massive mechanical systems resting directly beneath their feet. This engineering succeeds when it is ignored. It allows medical staff to focus on saving lives, unaware that the floor they're walking on is a high-tech bridge spanning a fault line.